Section 10.5 is about base e and the natural logarithms. The letter e is used to represent a number. This is what the number is, 2.7128, and there's more to it. Typically we usually just say 2.7, and that letter, that value, is called the natural base. And we can also have a natural base exponential function that looks like this: y equals e to the x power. You see the graph of it over here. This letter e is a useful letter in upper level mathematics, and there's even a button on your calculator to find out what e to whatever power is. So you should know how to type this into your calculator, e to the second power, and you should get about 7.3891. If you do e to the negative 1.3, you should get 0.2725. So please learn how to type the natural base, the e, into your calculator and do exponents with it. Now, to go along with the natural base, there's the inverse of that, which is called the natural logarithm, and that's a logarithm with base e. Now, you could write it this way: y equals log base e of something, but to make things even more confusing, there's a special way of writing it, and it's this way. It's called the ln, so y equals the ln of x. And the ln is the natural log function, which is the inverse of the natural base. There's also an ln button on your calculator. It's usually right next to the e button, so it's probably, actually it might even be the same button. You should know how to find the ln of 4. So if I type that into my calculator, I get a decimal approximation of about 1.3863. And you should be able to do that. Same thing over here. The ln of 0.05 is negative 2.9957. Now go down here, and we want to write an equivalent, either an exponential or a logarithmic equation. This one has the e in it, so we want to write the logarithmic version of this. The way I'm going to do that is I'm going to write this log base e of 5 equals x, and that's just using the definition of logarithms. Now I'm going to write that a little bit differently, because we said up here we don't typically write log base e. We use the shorthand version of ln. So we would say the natural log of 5 equals x. Over here we already have an ln, so we want to write this using exponential. So I'm going to write it this way: log base e of x is going to equal 0.6931, because that's what ln means, log base e. And now I'm going to write this using an exponent by saying e to the 0.6931 exponent equals x. So in this first one I had an exponential and I converted it to a natural log. Here I have a natural log and I had to convert it to an exponential, just to show you the relationships that the two have. Now, because the natural base and the natural logarithmic function are inverses, they undo each other, like squares and square roots and other things that we've seen. So if you have e to the ln power, those will wipe off and give you x equals x. And if you have ln of e, those will wipe off giving you x equals x. So if I go over here and I want to evaluate e to the ln of 7, that's just going to give me a 7. And ln of e to the 4x plus 3 is just going to give me 4x plus 3. It's that easy. They wipe each other out, and they can be used then to simplify expressions. So here's a problem in which we will use the idea of natural base and natural log to simplify this expression. I want to solve for the x, so I'm going to start by adding the 7 to both sides. So 5e to the negative x equals 9. I further want to isolate the e to the x by dividing both sides by 5. So get e to the negative x equals 9/5. Now to get rid of an e, I'm going to take the natural log of both sides. And when I take the natural log of e, they wipe each other out. So I'm left with negative x equals the natural log of 9/5. Last thing I'm going to do is just divide both sides by negative 1, giving me x equals the negative natural log of 9/5. So plug that into my calculator, get a decimal approximation. X equals the negative 0.5878. Here we're given a formula used to find continual interest, and we're going to use that formula to solve this problem here. We're depositing $1,000 and we're getting paid 5% annual interest compounded continuously. And the time that we're going to look at is 10 years. So I'm going to take my formula, A equals P times E to the RT. So my amount is P. P is the principal, what I'm going to start with. So I'm going to start with $1,000. And that's going to be E to the R. R is the rate. So I'm going to do 0.05 because that's the percentage rate. And the time I'm going to keep it in the bank is 10 years. So this is going to simplify. A equals 1,000 times E to the 0.5 exponent. That's a calculator problem. Type it into your calculator, say E to the 0.5 exponent, and then multiply by 1,000. And you should get approximately $1,648.72. Now in the second part, we want to know how long it will take the balance to reach 1,500. So we still want to take our $1,000. We're going to multiply by E to the 0.05 exponent. We don't know the time this time. That's what we're looking for. And we want to know when that value is bigger than 1,500. So this becomes an inequality. So I'm going to divide both sides by 1,000. So I get E to the 0.05t is greater than or equal to 1.5. And now I can get rid of the E by doing what we've learned here by taking the natural log of both sides, wiping that out. So 0.05t is greater than or equal to the natural log of 1.5. And now to isolate the t, I'm just going to divide by 0.05 on both sides. So that's a calculator problem. I can plug it in and find out that t is greater than or equal to 8.11. And we can know that it would take just over 8 years for the account to reach $1,500. Our last slide, we're given an equation and an inequality, and we're going to use natural base and natural log to solve them. Here I'm told the ln of 5x equals 4. Well, if I want to get rid of ln, I'm going to take both sides with a base e to those exponents. So that's going to wipe off here, leaving me 5x equals e to the 4th power, which I can then divide both sides by 5, and I get x equals e to the 4th power over 5. That's a calculator problem. I could just type in whatever e to the 4th power is, divide that by 5, and I'm going to get an approximate answer of 10.9196. So notice how the e cancels off the natural log. Likewise over here, I already have a natural log again. I want to get rid of it, so I take both sides with a base e, so e to the ln cancels, leaving x minus 1 is greater than or equal to e to the negative 2 power. Adding 1 to both sides, you get x greater than or equal to e to the negative 2 plus 1. So take the natural base to the negative 2 power on your calculator, and then whatever that is, add it to 1, and you're going to get greater than 1.1353. Now these should not be greater than or equal to's, but there's my solution.